I'm Calum McInnes, and thank you for the introduction. And today I'm going to talk to you about the potential for elastic tearing of composite aerospace structures by the fibre steering concept. So motivation-wise, why do we want to transition from conventional straight fibre laminates to this more novel fibre-steered concept? Well, as we all probably appreciate, the use of advanced composite materials in aerospace is rapidly increasing from the conception in 1940s to more or less the current year, kind of 2020-ish. In both the civil and defence sectors, we see there's certain aircraft such as the Boeing 787 Dreamliner using significant amount of composite material in primary structures such as fuselage, wing sections, and ailerons. So in terms of enabling new aircraft, one of the key design drivers is mass efficiency, whereby if we have mass efficient structures, in the case of, say, launch vehicles, this will allow for larger payload capacities, or in the case of aircraft, this will allow for lower fuel burn and a more sustainable aviation. And overall, it will enable kind of new market opportunities and more economic growth, which is always a good thing. So I've talked about this idea of fibre-steered composites, but what exactly are they? Fibre steering is quite simply the idea of having a non-continuous fibre angle across the planform of a ply. So conventionally, say in the case of quasi-isotropic design, we're stuck with 0, 90, plus minus 45. Whereas now, we could have a fibre angle that varies on the ply, and as such, we can redirect load paths and we can produce variable stiffness structures to enable some quite interesting and fairly weird designs. So, as Ian mentioned, my work considers fibre steering by the continuous toe shearing process, which was developed here at the Bristol Composites Institute. The CTS process shears material toes in plane compared to the conventional bending of other steering methods, and also allows perfect tessellation and eliminates potential defects. So another byproduct of this CTS process is that if we were to shear material in plane, material volume conservation dictates that that's accompanied by an out-of-plane thickness increase, and as such, in addition to a fairly low steering radius of the CTS process, we can design periodic fibre reference paths, and as such, we can have regions of periodic thickness build-ups on the structure, which start to kind of look almost like longitudinal stringers on a panel. So for this presentation, to highlight this concept, I want to strip it all back, and we're going to talk about just a simple problem in the case of a simply supported plate under uniaxial compression. This is fairly standard aerospace design, and I want to kind of illustrate a couple of concepts in which we could use fibre steering to improve the performance of our panels. So yeah, the overall hypothesis is fibre steering worthwhile more specifically on a mass efficient basis. So for this problem, I'm going to apply an end shortening to our panels, and this is going to be our sort of design load. And we're going to look at a couple of concepts and see, can this hypothesis be met? So in terms of designing for mass efficient load carrying capacity, I'm considering balanced and symmetric layups, so equal number of plus minus angles and symmetric stacking sequence about the mid plane. Another key point is there's no buckle-phobic design constraint, so the panel is allowed to buckle and we're allowed to exploit the non-linear region of the structure for additional load carrying capacity. So tailoring-wise, I've conducted it on 8-ply laminates, and it's probably best if we actually just avoid this sort of notation here because it just gets detailed very quickly. So I'll talk you through this particular plot. There is 3 variable stiffness structures denoted by VS 1 to 3. There is a quasi-isotropic structure, and there's also an angle ply structure. As you can see in the case of VS 1, we have some fairly substantial increase in load carrying capacity when compared to the quasi-isotropic design, which, if you look in the vertical axis, the results are normalized by mass. So per unit mass, how much force can this structure take? And as such, the variable stiffness or the fibre-steered structure can take more, which is good for our concept. Likewise, another interesting point to note is that the stiffness loss after buckling is less on the variable stiffness structure than the quasi-isotropic or angle ply one. So in our variable stiffness structure, we have fairly low decrease in gradient pre and post buckling, whereas on our conventional straight fibre, we have quite a substantial drop in stiffness. So overall, these fibre-steered panels can both increase and delay the buckling load. We can improve the post-buckling stability, and we can also increase the mass efficiency in terms of load carrying capacity. So overall, this is a fairly high level, kind of highlights real whistle-stop tour of this fibre steering concept. There's significant scope for performance tailoring in terms of playing with the elastic properties of our structures. We have a fairly substantial increase in design space, and overall, the fibre-steered structures are much more mass efficient. Future work aims to deploy some sort of formal optimization techniques in the meta-heuristic sense, such as GAs or surrogate modeling, to identify a true solution space optimum design. And I want to add some complicating features, such as a central cutout, which makes the problem much harder and could introduce some fairly novel routes. So I want to thank you all for your attention today. If there's any questions, I can take them now, or please do come find me at my poster. Thank you.
Thanks, Calum.
Thanks, Ian.